assignment. So homework 5 is due on Wednesday of next week. And so let's take a look at some of the problems on here. The first one is a disinfection question where we're looking at the rate of disinfection using Chick's law. And so Chick's law says that the rate of killing of microorganisms is proportional to the number that are present, and that there is a declining rate of inactivation as the number of microorganisms decreases. So Chick's law takes into account that declining rate with a logarithmic function. And what we know from the given data here is a chlorine concentration of 4 milligrams per liter for 3.5 minutes is causing a reduction in the viable population of pathogens from 85,000 initially, so that's N naught, down to 11,900. So what you're having to do in the first part of the problem is calibrate the K, the inactivation rate constant. And the problem says to assume a dilution coefficient of 1. And you should use the dilution coefficient of 1 for both concentrations of chlorine here. For the 4 milligrams per liter of chlorine, and then also in problem 2 where you're going to be applying the inactivation rate constant that you determine in part 1, you should still use the same dilution coefficient of 1 in Chick's law. So problem 1 is just calibrating Chick's law with given population data. And then in problem 2, which is related, you use the K sub CW that you've determined and estimate the duration that's required for 4 logs of removal. Now 4 logs of removal sometimes would be called 4 nines of removal. It just means that of the starting population, 99.99% of that starting population has been inactivated by the exposure to chlorine. So it's going to be longer than this 3.5 minutes from problem 1, because problem 1, that's not even 2 logs of removal to go from 85,000 down to 11,000. So for the first, you're having a greater inactivation between problem 1 and problem 2. But then the second aspect of it is that the chlorine concentration is lower. In problem 1, the chlorine concentration was 4, but what Chick's law allows you to do is play around with different combinations of concentration times time. And so in the second problem, the concentration is reduced to 3 milligrams per liter. So just a little bit of practice that has to do with chlorination. Any preliminary questions having looked at that?
How can you tell that you get 4 logs of removal again?
Well, 4 logs of removal is specified in the problem statement.
Mm-hmm.
So the way that you'd know is if the starting population was 10,000 and the finishing population was 1. Yeah, so 4 logs of removal or 4 nines of removal means 99.99% inactivated. And so if you multiply 10,000 by 0.9999, then I think what comes out of that is that there's just 1 which is viable, and 9,999 were killed. So in problem 2, what you're substituting into this ratio is basically a numerical reflection of the 4 logs of removal. Okay, now problem 3 is also related to disinfection, and we did an example in class that was related to UV irradiation. And so I don't want to go into too much detail on this. If you want to refer back to the recording, I think that that's going to be posted on YouTube. But the only thing that I've changed around a little bit is in that example we looked at in class, the flow rate was given and you were calculating the power. Here, the power is given, and so the unknown is how much water can you put through the reactor and still achieve the needed dose. Remember that in the case of UV, it's similar to chlorine in that dose is intensity times time. So in the case of chlorine, the intensity is the concentration of the chlorine, and then time is time. In UV, instead of having a concentration of a chemical, what you have is an intensity of radiation. And so the intensity of the radiation, what you're going to do here is calculate the power of the lamp, and then using the efficiency factor, convert that into the power of UV that's actually being shined into the water. And then the place where the UV intensity is the lowest is on the outside surface of the, well, I guess it's on the inside of the reactor, but if we think about a cylindrically shaped reactor as being in the middle is a bulb that's shining in all directions, the UV intensity is lowest the furthest away you get from the bulb. And so on the outside edge of the circle that is described by the reactor itself. So I think, there's just similar geometry as that other example. Just the difference is that now you're having to calculate the amount of time the water should spend in the reactor, because a joule is a watt second. And so you'll figure out how much time the water needs to spend in the reactor, and then given the reactor's volume, you can calculate the flow rate that should go through it, because flow rate Q, of course, is volume per time. And so we know the reactor volume because we have its dimensions. It's a diameter of 50 centimeters and a length of 2.2 meters. So the volume you can calculate directly, and then how much time the water should spend in the reactor is what comes out of your intensity calculations, the calculations that have to do with the UV irradiation that's required. If you're trying to hit a dose of 40 millijoules per centimeter squared, then that tells you it should be a certain amount of watts for a certain amount of time on that outside distance furthest away from the lamp. Okay, so that's problem 3. Problems 4 and 5 is just kind of an acknowledgement that we didn't get through all of the specific constituent removal types that are addressed in the textbook chapter. There are a couple of things that I think are important that we didn't have time to talk about in class, and so problem 4 is about nitrate, and I just want you basically to read the book section, and if you choose, just a quick Google search to figure out why are we worried about nitrate. And then problem 5 is about endocrine disrupting chemicals and pharmaceuticals. And this is kind of an emerging topic within water treatment, where for obvious reasons you don't want to be taking pharmaceuticals that aren't prescribed to you, but because a lot of pharmaceuticals end up in wastewater and wastewater is discharged to rivers, there are things like ibuprofen, caffeine, and even birth control chemicals that are detectable in drinking water sources, and they get into the drinking water in low concentrations, but it's an issue nonetheless. So problems 4 and 5 are just about some of the specific constituent removal issues that we didn't get a chance to talk about. Problem 6 has to do with the sludge and residual concentrations we talked about last time in class, and problem 7 is as well. So problem 6 is just trying to relate the volume of sludge to its mass, and then problem 7, you'll notice, is 20 points. I expect that that one may be a little bit more lengthy because I'm asking you to consider both the chemical cost of coagulation, but then also the disposal cost of alum versus ferric chloride. And let me go back to a formula that I showed you last time, where we're trying to estimate the volume of sludge that's generated. There are these equations that say that the dose of either alum or ferric chloride plus the amount of suspended solids that are being removed, plus miscellaneous chemicals that are being added. All of this can be accounted for and then estimate the mass of solids that are being generated through the coagulation sedimentation basin. And so then if you know this mass of solids and you know some of the characteristics like the sludge specific gravity, the amount of water, then you can find the volume of sludge. So this problem 7 is just kind of an economic analysis where if you're given a sludge disposal cost of $55.36 per cubic meter, and you know the cost of ferric chloride, the cost of alum, then I'm asking you to consider basically which is better to use for coagulation, the alum or the ferric chloride, because each one of them is going to require a different dose to achieve the same finished water turbidity, and each of them is going to generate a different amount of sludge. So steps A through H just kind of step you through the thought and analysis process that has to do with determining the cost of treatment for these two different coagulants. All right, so that assignment you've got until Wednesday next week. Today what we're going to be talking about is storage and distribution systems, and this is some of the material that's found in Chapter 17 of the textbook. In demand estimation and trying to figure out how big pipes should be and how much water needs to be on hand to satisfy demand, one important safety factor that we have to provide is extra capacity in case of fire. And our book goes into some detail talking about the benefits of automatic fire sprinkler systems and how it's an innovation that over the last 100 years has made fires not only less likely, but also has reduced the amount of economic damage and the number of people who die, because automatic fire sprinkler systems, they work regardless of human error, and they only saturate portions of a building where the fire and the heat actually indicates a need for water. Whereas if you have the fire brigade come out and they're just spraying the entire building down because they don't necessarily know where the fire is when they're on the outside of the building, so they may use a water cannon, break out windows, and send water into all different parts of a building to prevent it from spreading. Automatic fire systems will generally only sprinkle in a room when heat is detected in that room. So it puts the fire out, for example, in here and preserves all the other classrooms, and then there's less damage and less repair and recovery work that needs to be done in the rest of the facility. So they're great. But we need to make sure to provide into the building and into the pipelines that are providing water to the building enough water so that there isn't a huge pressure drop in case of a fire incident. And so one of the figures that our book illustrates is different classifications of hazard risk. And obviously if you have, for example, a warehouse that's holding flammable materials, then the amount of water that would be needed in case of a fire is much higher than just maybe an ordinary industrial building or residential structures where there's going to be a lot less quantity of flammable or potentially explosive things. So there's different groupings and categories and then extra hazard groups, and based on the area of protection that's being provided, what you'd do is you'd go to the classification. So for example, a building like a warehouse that has some manufacturing could be classified in group 2 or 3 depending on the materials that are used. If it's a warehouse that is built out of flame-resistant materials, or depending on the types of activity, would put it into one of the 2 categories. And then you would find the area of protection on the left-hand side of the vertical axis, intersect with the graph, and then you'd go down to what they're calling here a density, but what it really is the flow rate per square, either down at the bottom, square foot of building, or at the top, they just have the SI equivalent in terms of square meters. So the amount of water that you'd need to provide in case of a fire would be the square footage that's being protected multiplied by this factor that you get off the horizontal axis. So it's relatively straightforward, but what's a little bit more complicated is ensuring that there is enough duration of protection available. And compared to the usual demand for water, a fire has the potential of completely exhausting the elevated water storage tank that is often used to provide pressure, especially in places that are relatively flat and don't have a gigantic reservoir up on the hill around the outside of town. Sometimes small towns will have an elevated water tank, and if you have one of these extra hazard groups that requires a really large flow rate to fight a fire, these are typical values here. So for a typical facility that's extra hazard group 2, they need 38 cubic meters per minute to fight a fire, and you need to plan on 120 minutes. And so they're expecting that the fire potentially could take 2 hours to bring into control. And so if you multiply those two things together, 38 cubic meters per minute and 120 minutes, what we're saying is that you need to be able to have 4,560 cubic meters of water available to fight that fire. So it may mean that you have to have really large pumps available to generate enough pressure, because it's unlikely that you'd be able to have so much elevated storage as that. So the pumps would have to be much, much larger than the pumps that need to be in place just for the ordinary residential demand. So the planning phase is really important, and zoning regulations of what kinds of things can be built and where. Knowing that information in advance when the infrastructure is going into the ground can really be useful, because after the fact it can be extremely costly to put in extra firefighting capacity if land is rezoned. And here's another table from our book that shows some typical flow requirements for different types of structures in a fire in terms of an hourly basis. If you have adjacent structures that are close enough together that the fire could be communicated from one building to another, sometimes those areas are merged together. Hopefully there's not such a proximity that the fire could spread from one building to the next, but especially in really crowded industrial areas like New York, where they have a lot of factories and warehouses along a waterfront, it is common to have buildings immediately adjacent, and that's why some of these fire flows are so much larger than you might expect to see on just a single building basis. Where if you're talking about the central business district, which has a really high occupancy factor and really high density, then additional protection is provided, because it's not just going to be a single building that catches on fire. A bit more background about how these flow demands are calculated is that there is a National Society of Fire Protection and different government regulators have developed ways of calculating the needed fire flow at a location. And it's just interesting, I think, to look at the different factors that are taken into account when determining the amount of water that could be required to fight fires. They're looking at everything from the types of materials that are used in the building. So you see here it's talking about the construction factor would include the size of the building, but then also the type of materials used. And increasingly, it's becoming common for wood to be used on structures up to 5 stories tall, where in the past they wouldn't necessarily build wood structures that tall. They found safe ways to do it, and the design sophistication is such that the most common building size that's going up in a lot of medium-sized towns is to have a first floor that's block or concrete, and then up to 5 structures of wood on top of that. So because there's so many buildings that are being made with wood nowadays, the construction factor is something that they pay special attention to based on the fire flows that could arise from that. The occupancy factor looks at, in some ways, the way that the building is being used and the potential risk for human life if there's going to be, for example, a hotel where the number of people in such a small space is relatively high. It may be important to have a sprinkler system in each one of the rooms, where compared to a larger room, you could have a sprinkler system that covers a larger area and maybe you wouldn't need as many of the sprinklers. The exposure factor is looking at factors having to do with the types of materials that are inside of the building. And then the communication factor, sometimes also called proximity factor, just looks at how close to other structures the building is and how likely it is that a fire at one location could spread to another.
Does it not take into account location, like we're in West Virginia, California?
Yeah, that's a good question. I'm not sure if
Or does the
there
ordinance
are,
change?
I don't know if there is local variation. I mean, I would assume that there's probably like city ordinances in some places that are more strict than this baseline national standard, but I don't know if the national standard itself varies from place to place. But in calculating the construction factor, they take into account the size of the building area. And by the way, our textbook has these formulas, but for example, the equation for C sub I is a little bit different simply because of units conversion. Some of the NFF equations are based on liters per minute, others are based on gallons per minute, gallons per second. So if you notice some difference in the equations, it usually just have to do with units conversion. This one is based on SI units, and so the building area here would be in terms of square meters. And then the F value, the construction coefficient, you can see how different types of construction materials could scale down the fire requirements. And so if the F value is proportional to C, and C value directly inputs the needed fire flow, what you can see is if you had frame construction compared to fire-resistant construction, you may have 3 times as much needed fire flow. And then the same thing is true about the occupancy factor, that if you are storing materials that are non-combustible, then the occupancy factor is going to be much lower than things where rapid burning materials like flammable paints or upholstering shops where they have a lot of fabric and the material that's used to stuff inside of couches, batting, which is all flammable. So all these things are taken into account, and though you're unlikely to do a fire flow analysis for a building, I think it's important to be aware that you may design the size of a pipe that's going into a certain neighborhood, and just because you sized a pipe into one part of town based on the size of the area, the land use area, it doesn't necessarily mean, even if the same number of buildings are going to be in a different part of town, it doesn't mean that the fire demands could be the same, because there could be variation in the types of materials that are used for construction. There could be different uses for the buildings, and all of those things combined together collectively could mean that one part of town needs 4 times as much water for fire protection as another. So there's a possibility for really widespread variation in fire demands from one location to the next. And it's important just to be aware that you need to be really cautious in making assumptions for fire flows, and make sure that the people who are estimating the fire flows are licensed, and there is a fire protection licensure in the same way that there's licensure for civil engineering at the state level. The distance between buildings is another one of these factors that can really affect the amount of fire flow. If you have a distance of more than 30 meters between buildings, then the fire flow could be 1/3. of what's required if the buildings are less than 3.5 meters apart. This morning I was watching a new documentary that's on Netflix about the earthquake that happened in Nepal back in 2015. Maybe you've seen it in the top of your queue if you're spending time on Netflix, but they had an earthquake there, and anytime there's earthquakes, fires often follow because there's often, gas lines get ruptured, and then electrical lines are severed, and so earthquakes and fires kind of go hand in hand. And in the central part of Kathmandu, which is the capital of Nepal, they have just buildings packed together with very poor regulations, and you can kind of see that reflected in the fires that happened after the earthquake. There is a interesting cutaway here of a fire hydrant, and I don't think I'd ever necessarily seen what it looks like inside of a fire hydrant. The interesting thing is that here at the top, where the wrench would go, it's just transferring that turning really far down below the ground level is where the valve actually is. So the water would enter the fire hydrant after the valve is turned, and water down at the pipe that's coming into the hydrant below the ground level then flows up. And so everything that you see above ground is essentially hollow. There are these caps at the end that the hoses could be attached to go to a truck, a pumping truck, but the valve itself is below ground. Kind of interesting to see. You may occasionally see some fire departments will do it themselves, others will have the water company do it. But we were talking about iron and manganese and how they have the potential of coming out of solution because they precipitate and they can clog pipes. And so especially if the fire hydrant is at the end of a line, at the end of a water line, and there isn't water being used very often, then even if it happens slowly, there can be enough precipitation of iron and manganese that it clogs the pipe. And so it's a pretty common practice in places that firefighters will come out and flush the hydrants occasionally, especially at these locations that are kind of dead end or neighborhoods that they've put in the fire hydrants but there aren't people living there yet. So there's just a lot of stagnant water. In that stagnant water, the minerals can precipitate out, and it doesn't have to be precipitating onto the pipe, which would be kind of like a fixed precipitate. It could be that it's particulate precipitation that's settling down to the bottom, and enough of that over a long enough period of time, it's been a problem where they would open up a fire hydrant and no water would come out, simply because there's clogging of all the precipitation upstream in the pipe. Okay, minimum acceptable pressures. This is really a timely, this is at the forefront of my mind. You heard my cell phone ring just a minute ago. That's a plumbing contractor who's calling me because the water line at my house from the road up to my house is, it's got a leak for probably the last 3.5 weeks, I guess. I got a bill from West Virginia American Water for quadruple what I normally pay for water because there's a leak it's about 400 feet from the street out to my house. And I guess they don't call you, they just send you the bill. Hey, you've got a water leak. So I called the plumber to come out, and the plumber was thinking he could save me a little bit of money by using a 3/4 inch pipe. Right now what's in there is a 1-inch pipe, and I guess to someone who doesn't do hydraulic design it seems like, well, it's almost as big. 3/4 inch is almost as big as 1 inch, but I actually did the calculations yesterday. I did both Hazen-Williams equation and the Darcy-Weisbach equation, and there will be a 5 psi drop if I stick with 1-inch diameter pipe, or a 20 psi drop if I go to the 3/4 inch pipe. And the water pressure to begin with is only about 50 psi at my house. And so if I go with this smaller pipe, it'll be the sort of thing that if one person flushes the toilet while you're in the shower, that suddenly it changes temperature because the pressure drops so suddenly. So I'm going to go ahead and spend the money and get the 1-inch pipe instead of the 3/4 inch pipe because I want to maintain a good acceptable pressure. When you have a lot of demand, the pressure is going to decrease because there's more head loss through a pipe as the velocity through the pipe increases. And I know that there's, in this classroom right now, some people who have already taken hydraulic engineering and some people who won't take hydraulic engineering until this coming spring. So there's like a diversity of backgrounds when it comes to understanding like friction loss principles. But pressures too much above 650 should be avoided because in that range is when you can start to see leaks at fittings that don't have them tightened down all the way. A lot of water heaters will begin to leak around up and above the 850 kilopascal range. But when you're experiencing the maximum hourly demand, you don't want to go below 240 kilopascals unless there is a fire or emergency situation. Because when the pressure drops too low, it's possible that you can have backflow. That is that, you know, you'd open a valve in one location and that water would actually go into the pipe instead of out of the pipe. And that can cause contamination. So if at the road the pressure is only 140 kilopascals, that means roughly that if you had someone whose water was 14 meters above that, if they open up their faucet during this fire situation, then it could be suction situation, so that if that faucet was down into like a basin of dirty water, then it could draw that dirty water into the pipe and contaminate it. So that's why we worry about these minimum acceptable pressures, in part so that it delivers a high enough flow rate to the hydrant during a fire situation, but also it has some implications having to do with water quality and the risk of contamination. And so I know that this is a figure that those of you who have taken hydraulic engineering have seen before. Well, let's just talk a little bit about demand variation and the fact that the use for water isn't steady throughout the course of a day. Even though a lot of times we will quantify demand on an average daily basis in terms of like how many cubic meters of water is required per day, it varies a lot during the course of that 24-hour period. And so here is kind of an illustration of one typical temporal variation for water, a diurnal temporal variation where there's a set of peaks in the morning and in the afternoon, corresponding to, you know, people waking up and using some water before they go to work, and then water demand being a bit lower during the day when people aren't doing things like washing clothes and dishes and watering lawns and cleaning cars and so on. And then in the evening is when the water use is its highest. So there are peaking factors that can be dependent on how big of a town you have. You know, a city like New York City that they say never sleeps and, you know, people are always up somewhere, it's going to have less peaking than a small town, where in small towns more people are on the same kind of cycle because there are fewer employers, there's less geographic distribution, and so usually peaking factors in smaller communities are more pronounced than peaking factors for larger communities that are spread out over a larger area and have more variety in their industrial base and in the working hours that people keep. But these typical values are good enough just to illustrate a couple of points having to do with this temporal distribution. So just to get some early experience on this, or as a review for those of you who have already taken 331, let's consider the case of a town that has 5,600 residents. So this is the capita, the number of people in this town, 5,600. And what we assume is that each one of them on average uses 0.22 cubic meters per day. So with the population and the per capita estimate, we need to figure out what is the average daily demand for the town and then using the peaking factors, calculate the maximum daily and hourly demand, and then also the minimum hourly demand. So let me pause for a moment and give you a chance just to get some additional practice using these principles of peaking factors. So max day 25.6 liters per second, max hour 46.3 liters per second. And what about for the minimum hour? 4.28 liters per second, right. So during the minimum hour, you're likely to have the pressure at each point in the system be pretty close to the static pressure, meaning if there was no demand. But then during the maximum hour, we want to make sure that these pressures don't fall below the minimum during the point at which the maximum water is needed, both for the water use that's going to be there from the residential variations, but then also on top of it, the fire demands. So extending this analysis a little bit further, let's say that the maximum demand, which we just calculated, was at 7 p.m. So here's 7 p.m. on this figure, and what we just calculated was the 7 p.m. is 46.34 liters per second. Now, this figure is saying it's 275% of the average day at 7 p.m. So this is probably bringing back memories for those of you who did the project in 331 last year. I guess it was maybe earlier this year. It wasn't last year. It was just in April. And you're saying really good ones?
Not good ones.
Yeah, really good ones, just like you said. All right, so Q max, which we just found, is 46.34 liters per second. And that's at 7 p.m. when, according to the scale, it's 275% of average day. Okay, now what we can do is we can assume what would be the demand at 4 p.m. by looking on this figure. At 4 p.m., what is this crossover point as a percent of the average day? So if this is 150 and that's 200, like in the middle would be 175, so 60, 70, 80. It's about 195%, I think. So 4 p.m. is 195% of average day. And so Q, the flow rate at 4 p.m., would be this anchoring point of 46.34 liters per second multiplied by the ratio of the flow rates, 195% divided by 275%. So we're just linearizing. We're saying this is a scale, and by reading off the vertical intercept here, the percent of the average day, we can find out the flow rate at any time of the day. So 46.34 times 195 divided by 275 would mean that the flow rate at 4 p.m. is 32.9 liters per second. And then the flow rate at 2 p.m., we can do the same, 2 a.m. So 2 a.m. is in the middle of the night when it looks like, so 50, 60, 70, 80, that's maybe 90%. So Q 2 a.m. would be 46.34 liters per second. And then we have 90% divided by 275%. So the point is if you know in absolute terms any point on this curve, then you can find the flow rate at any other time of the day if you have a curve of the temporal distribution. So at 2 a.m., the flow demand approximately is going to be 46.34 multiplied by the ratio of 90 to 275. 15.2%. I'm not percent, liters per second. All right, real quick, let's just take a look at some different storage tank examples. Here is a storage tank that's above ground, but we don't have any way to inspect the bottom of the tank, the underside of it. And so there could be a small leak from the underside of the tank, and it wouldn't be immediately visible in the same way that it is for an elevated tank. And the other advantage of an elevated tank is it's a way of providing consistent pressure to the network, where if you're providing pressure to the network with pumps, the pressure only exists as long as the pump is on. And during periods at night, for example, when the demand is low, you don't necessarily want a pump running that is a pump that you'd use for the maximum part of the day. So in this example we just worked, we found that during the max hour, we're going to need 46 liters per second, but overnight we only need 4 liters per second. So you wouldn't necessarily want to have a pump running all night long that's sized to provide 46 liters per second if during the evening you only need to have enough water going for 4 liters per second. So one way around that conundrum is bring water up to the tank as needed, allow the pump to cycle on and off, and then the pressure in the network depends just on how highly elevated the tank is. So this, you can see, has a series of different structural supports. A fluted water tower is similar to a corrugated metal sheet that's been joined together to form a column. And so rather than multiple structural elements, there's kind of like a single sheet of steel around the outside that provides the structural support for the tank that's at the top. And then the inside part is hollow for pipes to go through it as needed. If you've seen these before in the asphalt, they are access to gate valves. And so you'll often see them in threes, because if you have a main pipeline and then a secondary line that branches off of it, you'd need to be able to close off the pipe at all 3 locations upstream and downstream of that junction. So you'll often see these gate valves in groups of 3. And I've never taken the lid off one, but now I'm kind of maybe interested to see what they look like. If there's a lid, I want to open the lid and see what's down there. So yeah, maybe we'll have some sort of a field trip. All right, well, it's 12:50. We're out of time. Remember that you've got a homework assignment in the queue. So hope you have a good weekend, and I'll see you on Monday.